We tend to imagine the ocean floor as stable ground, simply deeper water resting beneath us. But in one region of the South Pacific, the seafloor does not rest at all. The Tonga Trench drops more than 10,800 meters, deeper than Mount Everest is tall. If that mountain were lowered into this trench, its summit would still vanish beneath the surface. Depth stops feeling like distance. It becomes a force. At the bottom, pressure exceeds 1,000 times the air pressure at sea level. Every square inch endures more than 16,000 pounds, pressing inward without pause. Steel yields there. Glass fails. A human body exposed at that depth would not survive even a fraction of a second. Sunlight fades within the first 1,000 meters. Beyond that boundary, there is no natural light, only darkness shaped by weight and cold. The trench lies along one of the fastest converging tectonic plate boundaries on Earth. The Pacific Plate is being driven downward several centimeters each year, forced beneath its neighboring plate in a movement that never truly stops. The planet is folding into itself here. Some of the most powerful earthquakes ever recorded have originated in this region. Others begin hundreds of kilometers below the surface, in rock subjected to pressures few laboratories can reproduce. Unlike the Mariana Trench, this trench has seen far fewer human descents. There are stretches that have never been directly observed, mapped in outline but not in detail. We have clearer images of parts of Mars. When submersibles descend, their hulls creak under compression. Instruments often return damaged, if they return at all. Communications thin and distort as signals travel through dense water. If something fails at 10,000 meters, rescue is not possible. But what does it mean to explore a place where the ground itself is moving? Why do earthquakes begin so deep beneath this trench? How does steel endure long enough to measure anything at all? And what survives where pressure alone should make life impossible? Tonight, we descend toward the deepest silence on Earth. But before we begin, if you enjoy these calm explorations into the deep sea, I would appreciate it if you gave this video a like and perhaps tapped subscribe. It helps other curious dreamers find their way to this peaceful little corner of the internet. And if you'd be so kind, let me know in the comments, where are you listening from tonight, and what time is it where you are? It's always a joy to see how far across the world this little sleepy corner of science travels. Now take a slow, deep breath, let your shoulders soften, and together, let us sink carefully into the shifting depths of the Tonga Trench. Far out in the wide Pacific, where island chains trace faint arcs across the water, the seafloor bends in a long, slow curve that charts a boundary invisible from above. Ships pass without notice. Waves roll without pause. Yet far beneath their keels, two vast pieces of earth meet and press together in a motion so gradual it escapes ordinary time. The Tonga Trench rests along this hidden seam east of the islands that give it its name, marking a frontier where the Pacific Plate advances toward the Indo-Australian Plate. These slabs of crust are not fixed platforms, but drifting rafts of stone riding a softer layer below. Their movement is measured in centimeters each year, about the pace fingernails grow, though the force behind that drift carries the weight of continents. As the Pacific Plate approaches the boundary, its edge tilts downward and begins to slide beneath its neighbor. This descent is called subduction, though the word barely suggests the scale involved. A section of ocean floor hundreds of kilometers wide slowly angles into the mantle, drawn by gravity and by the density of its own cooling rock. Water trapped within its minerals travels with it, locked inside crystals formed long ago at the surface. Where one plate sinks and the other remains above, the surface folds into a deep trough. Sediments that once lay flat are dragged toward the bend, then spill into the depression like slow falling dust. The trench is the visible signature of that motion, a line etched into the planet where one chapter of crust slips beneath another and begins a long return to heat. This particular trench reaches unusual depths because the descending plate here is old, heavy, and cold, traits that make it sink more readily. Its path angles steeply, carving a sharper notch than many other subduction zones. The surrounding region also moves quickly by tectonic standards, so the downward pull is steady and persistent, like a curtain being drawn with unhurried certainty. Nothing about this boundary is fixed. The edge shifts as fragments break, as sediments pile, as stresses gather and release. Sections sink faster, others stall, and the contour subtly rearranges itself. Over years, the changes are slight. Over ages, they redraw the entire landscape of the seafloor, shaping ridges, basins, and slopes that no surface map can fully capture. Even the islands nearby owe their existence to this convergence. Melted rock rising from the descending plate feeds volcanoes that build land grain by grain. Ash settles, stone cools, and new crust forms above the place where older crust disappears. Creation and descent share the same narrow corridor, balanced in a cycle that has continued for millions of years. All of it unfolds in silence beneath the rolling Pacific, a patient choreography of stone guided by heat from deep within the planet. The trench is not merely a hollow in the seabed. It is a process made visible, a border where motion becomes landscape, and where the surface of the world quietly records the slow turning of its interior. Far below any charted horizon, the descending slab continues its quiet journey, heating, softening, and blending back into the mantle from which crust is born. Minerals transform, releasing fluids that rise into the overlying rock, altering its chemistry and lowering its melting point. In this way, the trench participates in a vast circulation, a planetary breathing in which surface and interior exchange, substance without haste, without sound, without end. Here the foundation of the trench persists, shaped by motion older than mountains and destined to outlast them all silently. Long before any vibration reaches instruments, the event has already unfolded in darkness far beneath the charted crust. In that unreachable depth, stone does not behave as it does near the surface. It flows, it transforms, it carries stress like a memory held for centuries. Beneath the Tonga region, some ruptures begin more than 600 kilometers down, within the descending slab that continues its slow descent through the mantle. At such depths, temperature rises and weight increases, until familiar rules of fracture seem they should fade. Yet sensors across the world record sharp pulses arriving from those hidden origins, signatures of sudden motion, where motion should be smothered. Geologists once believed earthquakes could not occur so far below, since immense pressure was thought to clamp rock so tightly that slipping would be impossible. Laboratory chambers can reproduce fragments of that compression, though never the full burden present inside the planet. When samples are squeezed and heated, their minerals rearrange into denser forms, crystals folding into new structures. This transformation can store energy, and when it releases, the change can ripple outward as a seismic wave. Within the sinking plate, ancient seafloor minerals still contain traces of water bound into their lattice. As depth increases, those minerals break down and release the trapped fluid. The presence of that fluid alters how surrounding rock resists stress, allowing sections to shift abruptly rather than bend. The motion is slight in distance, yet immense in consequence, a subtle slip magnified into vibrations that race through the globe. If a research vessel rests thousands of meters above while such an event occurs, the disturbance arrives not as a single jolt, but as a procession of traveling pulses. Sound moves efficiently through deep water, and seismic waves entering the ocean can couple with it, turning solid Earth motion into pressure oscillations that glide through the sea. A submersible drifting in the column would register these as low tremors passing through its hull, instruments flickering as sensors translate motion into numbers. Engineers design deep vessels to tolerate external force pressing steadily from all sides, though shifting waves of pressure differ from steady load. Materials flex by microscopic degrees, joints whisper against their seals, and delicate components must continue functioning while the surrounding structure absorbs the passing energy. The craft itself may remain secure, yet its readings can blur, navigation signals can wander, and fine measurements may dissolve into static. What lends these earthquakes their quiet gravity is their unpredictability. The descending plate does not fracture on a schedule. Stresses accumulate in patterns too intricate for present models to trace with certainty. Monitoring stations listen constantly, forming a global network attuned to faint stirrings below the crust. Yet even this attentive web cannot specify when the next deep rupture will unfold. So the region carries within it a hidden chronicle of shifting minerals and migrating fluids, each adjustment part of a slow interior dialogue. Most of the time, that dialogue remains inaudible to the surface world. Then, without announcement, a pulse travels outward from the depths, crossing mantle, crust, ocean, and instrument alike, a reminder that far below every shoreline, the planet continues its patient rearrangement. Those who study these signals learn to read them as one reads distant weather, noting arrival times, subtle frequencies, and fading tails that hint at their birthplace. Each trace inscribed on a screen represents a journey upward through layers no eye will see. In this way, the deepest earthquakes remain unseen, yet faithfully recorded, their passage preserved as lines of motion written quietly across listening instruments. Stone remembers, and the record endures. Numbers speak first when engineers describe the deep. At the surface, instruments read a single atmosphere, a gentle baseline that presses lightly on every object. With each 10 meters of descent, another atmosphere joins it, stacking invisibly, multiplying without sound or signal to human senses. By 1,000 meters, the tally has grown to 100 atmospheres, a weight equivalent to balanced locomotives resting upon a space no larger than a hand. Metal responds to such force in a language of strain. Under increasing load, its lattice compresses, atoms edging closer, imperfections tightening like knots in pulled rope. A flawless hull distributes stress evenly, allowing the burden to pass around it and continue outward. Yet, perfection exists only in theory. Real materials contain minute inconsistencies, regions where thickness varies or crystals misalign, and these small deviations decide the fate of descending machines. When pressure finds one of these weaknesses, it concentrates there, focusing its immense push onto a point no wider than a grain. The surrounding structure still holds, though the burden is no longer shared equally. At a critical threshold, the stressed spot yields, not gradually, but all at once. Water surges inward faster than sight, structure folds, and the vessel collapses before any signal can travel from hull to mind. Such events have occurred in testing chambers and open ocean alike, recorded not as spectacles, but as brief lines in engineering logs. Prototype housings have crumpled during unmanned trials, their frames returned as compacted shapes resembling crushed cans. Sensors lowered on cables have vanished when casings failed, leaving only slack line drifting upward. Each incident becomes a lesson written in metal and mathematics. To resist that fate, designers favor spheres for occupied craft. A sphere offers symmetry in every direction, so external force arrives evenly across its surface. Cylinders, though practical on land, invite imbalance below, their flat sections encouraging stress to gather rather than disperse. Curved geometry guides pressure around the hull, returning it to the water instead of allowing it to linger. Before any descent, calculations unfold across pages and screens, tracing how alloys will behave, how seals will compress, how viewports will endure their share of load. Equations account for temperature, density, elasticity, and time, since materials slowly deform even under constant force. Safety margins are drawn not as guesses but as narrow corridors bordered by certainty on one side and collapse on the other. Those numbers accompany every voyage, quiet companions to steel and circuitry. They represent foresight, shaped by past failures and patient experimentation. Long before a hatch closes, the outcome has already been weighed in symbols and proofs, each figure a small lantern of reason carried downward into the vast and pressing sea. Pressure at depth does not strike like a blow. It persists, it surrounds, it waits with infinite patience, testing every seam and surface without rest. This persistence shapes the philosophy of those who build vessels for such realms. Strength alone is not trusted. Balance is trusted. Uniformity is trusted. Even the smallest bolt is inspected as if it were a gate through which the ocean might enter. In quiet workshops far from shore, components rest beneath measuring tools that slide and blink with cool light. Surfaces are polished until friction finds no purchase. Edges are rounded so force cannot gather. Piece by piece, the craft becomes less an object and more an agreement with physics, a promise that every curve and thickness will answer faithfully to the immense arithmetic of the deep. Within that arithmetic, survival is simply the moment when structure and pressure remain perfectly equal together still. Before descent is ever permitted, a checklist is read in a quiet voice, not as ceremony, but as acknowledgement. Each line describes a boundary that cannot be crossed once the surface has sealed itself overhead. Depth is not the true barrier. Distance is. Modern rescue craft are built for shallower realms where cables can reach and guidance signals travel cleanly. Only a small number can operate beyond a few thousand meters, and even those must work slowly, conserving power, measuring every movement. The deeper a vessel rests, the fewer machines on Earth can approach it, until at extreme depth, none can arrive at all. Water resists communication as surely as stone resists touch. Radio waves fade within meters, absorbed by the conductive sea, leaving sound as the only reliable messenger. Acoustic transmissions move patiently, far slower than light, and they scatter as they pass through layers of varying temperature and density. A message sent downward may bend away or thin into fragments before it arrives. Inside a submerged craft, replies travel upward with the same delay. Seconds stretch between exchange and answer, then minutes as distance increases. Conversation becomes rhythm rather than dialogue, each statement released into silence, each response returning after a measured wait. In emergencies, that interval expands into a barrier as real as any wall. Should a vessel lose power on the seafloor, ascent cannot be improvised from above. Recovery ships must first determine position with precision, mapping a target they cannot see. Equipment is assembled, lowered, adjusted, then lowered again, each stage guided by instruments that interpret echoes and tension. The process unfolds gradually, since haste risks tangling lines or striking the stranded craft. Weather at the surface may slow the effort further. Waves influence cranes, winds shift cables, currents draw equipment off course. Days can pass while conditions settle enough for safe operation. All the while, those waiting below depend on systems designed to last, air reserves carefully calculated, batteries portioned like provisions on a long voyage. Designers understand these limits long before any mission begins. For that reason, deep vessels are created to function as their own lifeboats, carrying redundant controls, reserve ballast releases, and timed ascent mechanisms meant to trigger even if crews cannot act. Independence is not a luxury but a principle written into every circuit and valve. Those who travel downward learn these truths as part of preparation. Training does not dwell on danger, yet it traces every procedure, every contingency, until response becomes calm habit. In simulators and briefings, they experience silence, delay, confinement, and the steady passage of hours without outside contact. Familiarity turns uncertainty into something shaped and known. Acceptance settles quietly once understanding is complete. The descent then becomes an agreement between human intention and natural law, witnessed only by instruments and the slow-turning earth. Far above, support teams listen through their receivers, attentive to faint signals rising from below, aware that assistance grows more distant with every meter of depth. So the journey proceeds with care, sustained by preparation and trust in design, not because help stands ready nearby, but because it does not. In that knowledge lies the discipline of exploration, a still awareness carried downward alongside the travelers, as constant and invisible as the sea surrounding them. Above the waves, the sky may appear unchanged, clouds drifting as they always have, yet far below that calm ceiling, a fragile chamber moves through miles of water with no path for swift return. Its safety rests in foresight, patience, and the quiet precision of those who built it. Rescue remains a distant possibility there always. Nothing on the trench floor rests in permanence. What appears level in maps exists in motion, grains shifting, layers tilting, surfaces rearranging themselves with patient inevitability. The ground there behaves less like pavement and more like a drifting fabric, woven from fragments of shell, dust, and volcanic ash that settle, pause, and slide again. Sediment arrives from far away, carried by currents that wander across the basin and release their burden when they slow. Each particle sinks until it meets another, forming blankets so soft that their own weight presses them onward. When slopes grow steep enough, whole sheets loosen and begin to descend, not falling freely, but gliding, folding, and spreading as they travel downslope. These movements are known as submarine landslides, though the phrase hardly conveys their scale. Some involve volumes greater than mountain ranges, masses that shift with unhurried momentum until gravity finds equilibrium. The front edge advances, the rear follows, and the entire formation migrates as a single body, reshaping the contours it crosses. At times, the motion accelerates and becomes a turbidity current, a dense cloud of sediment and water flowing together along the seafloor. It moves like a storm pressed flat, rolling outward in a billowing front that can travel for many kilometers. Anything resting in its path is lifted, carried, and set down elsewhere as the current gradually thins and settles. The terrain, therefore, cannot be trusted to remain as it was. Ridges soften, hollows fill, and gentle inclines transform into sloping chutes of loose material. What seems solid under a descending probe may in truth be a layered drift waiting for disturbance, its grains poised like a crowd, ready to move at the slightest signal. Scientific instruments placed upon this shifting ground sometimes share the fate of fallen leaves. A sensor frame may stand upright when first deployed, its readings clear, its position certain. Months later, its signal fades, not from failure of circuitry, but from burial, as gradual deposits cloak it grain by grain until only a smooth plane remains above. Cables trailing behind drifting equipment can also sink into the soft surface, pulled downward by their own weight until they disappear from sight. Retrieval then becomes an act of patience, gentle tension applied in hope that the line has not been claimed entirely. Sometimes it returns coated in fine silt, sometimes it returns with nothing attached. Even without disturbance from above, the seafloor continues its subtle migrations. Particles settle into gaps, water slips between them, and the arrangement compacts. This slow compression can tilt objects, altering their orientation by degrees so slight that only careful measurement reveals the change. The landscape adjusts itself continuously, like a sleeper turning in rest. For researchers, charts of this region are always provisional, faithful only to the moment they were made. A survey passed over the same coordinates years apart may trace lines that no longer match, as though the pen had wandered. The difference does not signal error, it records the quiet travel of the ground itself. In this realm, stability is a temporary arrangement rather than a rule. The floor receives, shifts, and releases in cycles too gradual for hurried perception. Instruments, markers, and landers enter as visitors and remain only while the sediment permits. Around them, the plain continues its unending rearrangement, a slow choreography of particles guided by slope, gravity, and time. No sound announces these migrations. No boundary marks their progress. Change unfolds beneath notice, steady as breath. What rests upon this floor rests on motion, and what settles here joins a journey already underway since ages beyond memory. Light leaves the ocean in stages. First, the warmer colors withdraw, reds dissolving into gray, then oranges, then yellows, until only blue remains to drift faintly through the water. Even that final trace thins as depth increases, fading not abruptly but by degrees so gentle they escape notice. Marine scientists mark these thresholds with names. The sunlit layer gives way to the twilight region, and below that lies the midnight zone, a vast interval where sunlight no longer arrives. Still deeper rests the hadal realm, narrow and trench-bound, where darkness is not simply absence of light, but a constant condition that has persisted for ages. Human sight evolved for brightness scattered through air, for horizons and reflections, and the subtle edges cast by daylight. In the deep ocean, those abilities fall quiet. Eyes remain open, yet gather nothing, their pupils widening without reward. Vision becomes memory rather than perception, recalling brightness that is no longer present. Submersible crews rely instead on instruments that translate surroundings into symbols and tones. Sonar pulses spread outward and return as mapped echoes. Depth gauges trace steady figures. Compasses hold their patient alignment. These devices become a kind of second awareness, extending perception beyond what biology alone can manage. Artificial lamps can be switched on, and when they are, the beam reveals only a small circle before dissolving into opacity. Particles suspended in the water reflect the light back toward its source, forming a luminous haze that limits distance. Beyond that glow, space returns immediately to obscurity, as complete as if no lamp had shone. Because sight cannot guide orientation, navigation follows other senses. Pilots listen to the cadence of sonar returns, feel faint vibrations through the hull, and watch the slow drift of numbers across their displays. Movement is measured not by passing scenery, but by changing data. A journey described in digits rather than landmarks. Time also alters its character in such surroundings. Without sunrise or shadow, hours lose their visual markers. Clocks continue their steady count, though the mind receives no external signal to confirm their passage. Moments stretch, unanchored from the familiar rhythm of day and night, known at the surface. The darkness itself remains unchanged. It does not flicker or ripple, it simply endures, a uniform field extending in every direction beyond the reach of lamps. Creatures native to these depths accept it as the default state, many producing their own brief glows through chemical reactions within their bodies. These living lights appear and vanish softly, like thoughts passing through sleep. For visitors, adjustment arrives gradually. Training prepares them for limited visibility, yet experience carries its own quiet lessons. Attention turns inward, breathing becomes more noticeable, and small sounds gain clarity. The absence of visual distraction simplifies awareness, narrowing it to essentials. In this lightless expanse, direction, distance, and form are known through interpretation rather than sight. Darkness does not conceal the world, so much as translate it into another language, one spoken through echoes, readings, and subtle motion. Within that language, those who travel here learn to move with care, accompanied by instruments and by the steady cadence of their own thoughts. No horizon appears to mark position. Up and down lose their ordinary meaning, since gravity offers no visible cue and the surroundings provide no frame of reference. Orientation depends on gauges and inner balance, a quiet cooperation between human senses and crafted instruments that keeps motion smooth and deliberate. Here, darkness is not an obstacle but a condition, constant and unbroken, within which exploration proceeds softly, carried forward by patience, numbers, and attention to every sign. Discovery in the trench did not begin with shapes rising from the gloom, but with faint motions captured on remote lenses, movements so delicate they seemed at first like drifting debris. Only after careful review did researchers realize the particles possessed intent, each tiny form steering itself with purposeful strokes. Life was present even here. The earliest visitors identified were amphipods, small crustaceans related to shore-dwelling species, yet altered by depth into pale, delicate swimmers. They drifted above the sediment in loose gatherings, their limbs extended like fine threads sensing the water. Their shells lacked heavy armor, replaced by supple surfaces that yielded gently to surrounding force. Later expeditions revealed snailfish, living near 8,000 meters, their bodies translucent and soft, as if sculpted from clear gel. They hovered just above the seabed, fins undulating slowly, neither hurried nor still. Within them, bones had thinned to fragile frameworks, light enough to endure the immense load pressing from every side. At such depths, rigidity becomes a liability. Structures built to resist compression near the surface would splinter here, so evolution favors bodies that bend rather than oppose. Proteins fold differently, membranes grow more fluid, and internal cavities shrink until almost no empty space remains. Flexibility becomes a form of strength. Calcium that might form dense skeletons in shallow species is reduced, leaving frames that resemble fine latticework. This light construction prevents crushing, since pressure passes through witut meeting solid resistance. Muscles anchor to these delicate supports and move with slow precision, conserving energy in a realm where food arrives rarely. Color also fades from these inhabitants. Pigments serve little purpose where no light falls. So many species appear transparent or faintly white, their forms defined only by outline. Eyes often shrink or vanish, replaced by heightened sensitivity along the skin that detects subtle vibrations. For biologists, these creatures became living notes written by natural selection under conditions once thought uninhabitable. Each adaptation spoke of generations, shaped not by sunlight or seasons, but by weight, chemistry, and time. Anatomy here follows different rules, guided by forces that reward softness, patience, and economy of motion. The presence of such organisms confirmed that the trench is not an empty scar, but a quiet habitat. What survives there does so by yielding, by matching the surrounding force instead of resisting it. In their pliant forms lies a record of adjustment written across countless generations. Researchers, observing them from afar, noticed how calmly they moved, as if the immense burden above were simply another element like water or salt. Nothing in their motion suggested strain. They glided, paused, and glided again, sustained by bodies tuned precisely to their surroundings. Specimens brought upward for study rarely remain unchanged, since ascent alters the balance they evolved to match. Tissues expand, structures weaken, and the very traits that protect them below become sources of fragility above. For this reason, many observations rely on cameras and samplers that allow life to remain where it belongs. Through such encounters, understanding grows of how existence reshapes itself when pressed by extremes. Evolution does not hurry, yet given enough ages, it alters flesh as surely as rivers alter stone. The animals of the trench embody that slow artistry, carrying within their soft frames the history of adaptation. So the first glimpses of life in this depth did not arrive as spectacle, but as quiet recognition. Forms once thought impossible drifted gently through the dark, complete, sufficient, and entirely at home. Their presence rewrote expectation, showing that even here biology finds a way to endure. Silence keeps their secrets while they continue living quietly. Records of depth are often written in numbers, yet one record lives in the fragile body of a single fish. It was observed far below the ranges once believed possible for vertebrate life, moving slowly through water that would crush most known creatures. Its presence marked a boundary not drawn on charts but carried in flesh. This animal, a species of snailfish adapted to the trench, was documented near 8,000 meters, where pressure rises to levels that alter the behavior of molecules themselves. Proteins that give muscles strength and enzymes their shape begin to lose stability under such force. In most vertebrates, these molecules would twist out of form, halting the chemistry that sustains life. The deepest fish endures because its cells contain compounds known as piezolites, small organic molecules that steady proteins and keep them functional. These substances act quietly, surrounding delicate structures and preventing collapse. Without them, tissues would fail long before such depths were reached. Even with this, protection limits remain. As pressure increases, water is pushed into spaces within the body, compressing membranes and influencing reactions that nerves and muscles depend upon. Beyond a certain threshold, no biochemical adjustment can compensate. The very reactions that allow a vertebrate heart to beat and gills to exchange gases begin to falter. For this reason, fish are not found in the deepest hollows of the trench. Cameras lowered farther record invertebrates instead, organisms whose simpler bodies tolerate extremes that complex skeletons and organs cannot. Vertebrate design carries advantages in many environments, yet here it approaches a quiet boundary written by physics and chemistry together. The snailfish that holds the depth record does not appear strained by its surroundings. It drifts with gentle motions, fins spreading and folding like soft fans. Its skeleton is reduced, its tissues gelatinous, its form shaped less by speed than by endurance. Every feature reflects a lineage, refined to function at the edge of what backboned life can withstand. Researchers studying these animals note that their adaptations come with trade-offs. The same chemistry that stabilizes proteins under pressure can interfere with function in shallower water. Individuals brought upward too quickly lose equilibrium as internal balance shifts. Their survival depends on remaining within the narrow range their biology was built to match. Such observations reveal more than the habits of a single species. They outline a principle that extends across living systems. Life can adjust to remarkable conditions, though each adjustment carries cost, and each lineage inherits limits set by its structure. Evolution explores possibilities patiently, yet it does not erase the laws that govern matter. In the trench, that truth becomes visible through absence as much as presence. Where fish disappear, the boundary announces itself without sound or sign. No wall stands there, no change of color or texture, only a depth at which vertebrate form can no longer persist. So the deepest recorded fish remains both a discovery and a measure. It shows how far adaptation can reach, while also indicating where it must pause. In its quiet movements lies a record of biological resilience, and in the depth beyond its range rests a reminder that every form of life, no matter how refined, exists within conditions that shape and limit it. Beyond that margin, the water continues downward unchanged, though no vertebrate accompanies it. Pressure climbs, chemistry tightens, and possibility narrows until only the simplest anatomies remain. The boundary is not sudden yet, it is final, a gentle closing of a door shaped by nature, marking the point where backbone and depth part ways. There the limit holds steady in silence, always thereafter. Energy arrives here by chemistry rather than light. In the depths of the trench, nourishment does not descend from above in bright rays, but rises from reactions within the earth itself, where water and stone meet and exchange elements in silence. Certain microbes cluster along mineral surfaces, drawing sustenance from compounds dissolved in the surrounding water. They oxidize substances such as hydrogen sulfide, methane, and reduced metals, releasing energy the way plants release it from sunlight. This process is known as chemosynthesis, though the word only hints at its quiet elegance. Inside these cells, molecular pathways guide electrons from one compound to another, step by step, like beads sliding along a thread. Each transfer yields a small reserve of usable power, stored in chemical bonds that the organism can later spend. No glow marks the reaction, no warmth announces it. Yet it sustains metabolism as surely as daylight sustains forests at the surface. Colonies of such microbes form the foundation of communities that require no sun. They coat rocks, settle on particles, and drift in thin veils through the water, multiplying slowly. Around them gather other organisms that graze upon this living film, and predators that feed upon the grazers until a complete food web exists, anchored not in light, but in chemistry. The source of these reactive substances often lies below the seafloor, where circulating water interacts with buried minerals. As fluids move through cracks in the crust, they dissolve elements and carry them upward. When these enriched waters emerge, even gently, they provide fresh material for microbial growth. The exchange is steady and understated, yet it can persist for centuries. Because of this process, sunlight is not the universal requirement once imagined. Life proves capable of drawing energy from the planet's internal resources, provided the necessary compounds are present and conditions remain stable. The trench demonstrates this principle with quiet clarity, showing that illumination is only one path among many. Biologists studying these systems have come to see habitability less as a matter of brightness and more as a matter of chemistry. Where gradients exist, where molecules differ in energy and can be rearranged, living cells may find opportunity. The essential ingredient is not light, but imbalance, a difference waiting to be bridged. This realization broadens the map of possible living worlds. Environments long dismissed as barren may instead hold subtle activity, sustained by reactions hidden from sight. Beneath ice, within rock, or under distant seas, similar processes could unfold wherever liquid and mineral meet. In the trench, these truths appear in miniature. Microbial films persist on scattered surfaces, renewing themselves as slowly as crystals grow. They neither hurry nor rest, guided by reactions older than any organism that uses them. Their existence suggests that life is less dependent on place than on possibility. So the deep remains quietly inhabited, not by gardens of leaves or drifting clouds of plankton, but by minute chemists conducting ancient exchanges. Through them, the boundary of the habitable shifts, extending into regions once thought empty. And in their patient activity, the definition of a living world becomes wider, softer, and more inclusive than it once seemed. Within such quiet transactions, the planet reveals a different generosity, offering energy without flame or dawn. Chemical gradients replace sunrise, mineral surfaces replace soil, and time itself becomes the gardener. Nothing rushes, nothing calls attention, yet sustenance flows from reaction to cell, from cell to community, in an unbroken chain. Here, existence is powered by contrast alone, by the meeting of substances that long to change, and in that meeting, life continues quietly and ever steadily. Long after an object is discarded, its story may continue in fragments too small to see. In the farthest reaches of the ocean, researchers examining tiny crustaceans from trench depths found particles lodged within their bodies, bright under microscopes, angular and artificial. These fragments were microplastics, carried from distant shores and cities, delivered not by intention but by the restless pathways of water. The amphipods that contained them had never approached land. They lived their brief lives in sedimented stillness, feeding on organic traces that drifted down from above. Yet within their tissues appeared colored shards, threads, and grains shaped by industry. The discovery showed that material shaped by human hands had traveled nearly 1,000,000 meters downward, entering a realm once thought beyond such reach. Plastic persists because its molecular chains resist decay. Sunlight can weaken it near the surface, waves can fracture it, and time can reduce it. Yet, these processes rarely destroy it completely. Instead, the material breaks into smaller and smaller pieces, each one light enough to remain suspended until currents guide it elsewhere. Some fragments sink slowly after becoming coated with organic films, descending through layers of water like quiet snow. Ocean circulation provides the path. Surface currents gather debris into broad gyres, while colder, dense water masses slide beneath warmer layers and move along the seafloor. These slow rivers travel across basins, carrying dissolved minerals, nutrients, and stray particles alike. A fragment released near a coastline may join such a flow and wander for years before settling far from its origin. When that fragment finally comes to rest in a trench, it does not remain isolated. Bottom-dwelling organisms encounter it as they sift through sediment in search of nourishment. To them, the plastic has no meaning beyond size and texture. If it resembles food, it may be swallowed. If it settles nearby, it may become part of the shifting ground they inhabit. Scientists studying retrieved specimens began to recognize how widespread this distribution has become. Samples collected from multiple trenches contained similar traces, indicating that no basin is entirely separate from the global system of currents. The ocean connects its most distant regions through slow, persistent motion, linking shorelines to abysses without pause. This realization alters the way the deep is understood. Distance alone does not guarantee separation. Substances released at the surface can travel vast routes, guided by temperature gradients, salinity differences, and the turning of the planet. The same circulation that distributes oxygen and heat also disperses remnants of human manufacture. Within laboratory dishes, the particles appear almost decorative, flecks of blue or red against pale backgrounds, yet their presence in these animals tells a larger story about movement on a planetary scale. Each speck marks a journey completed, a path traced through invisible highways of water that span hemispheres. Far below, the amphipods continue their quiet existence, unaware of the origin of what they ingest. Around them, the seafloor receives a steady fall of natural debris mixed now with synthetic dust. Both descend together, indistinguishable in motion, settling side by side as they reach the lowest contours of Earth. In this way, the deepest habitats become archives, storing evidence of processes unfolding far beyond their boundaries. Layer by layer, sediments preserve what arrives, whether born of erosion, eruption, or invention. The trench accepts all with equal silence, holding within its strata a record of connection that binds the highest shore to the farthest depth. There it rests without judgment, a silent ledger of passage, reminding careful observers that nothing released into the world is ever truly lost to time itself quietly. Reputation often shapes the paths explorers choose. In the chronicles of ocean study, certain names gather attention, while others remain softly spoken, and this difference guides ships as surely as currents. Among the deepest places on Earth, one trench became widely known, its title repeated in textbooks and broadcasts, while another of comparable depth rested outside the brightest circle of notice. The Mariana region entered scientific memory early, when sounding lines first revealed an extraordinary descent in its floor. Later expeditions confirmed the measurement, and the location known as Challenger Deep became a symbol, a geographic superlative that captured imagination. Once a place acquires such distinction, it begins to draw continued visits, since each mission can build upon earlier charts, earlier instruments, earlier experience. Researchers planning costly voyages often favor destinations with established records. Familiar coordinates promise clearer logistics, reliable navigation data, and a history that helps justify expense. Funding agencies, balancing curiosity with practicality, tend to support projects that extend known narratives rather than begin entirely new ones. In this quiet arithmetic of budgets and proposals, recognition becomes a form of gravity. The Tonga Trench, though immense and dynamic, entered this story later and with less ceremony. Its remoteness from major research ports increased travel time, and its surrounding waters offered fewer convenient staging points. These details rarely appear in public accounts, yet they influence decisions long before a vessel leaves harbor. Attention from news and documentary circles also shapes exploration. Stories gravitate toward familiar names, since audiences recognize them instantly. Each article or film that revisits a celebrated site strengthens its presence in cultural memory. Meanwhile, other regions, equally remarkable yet less publicized, remain in comparative obscurity, their outlines known mainly to specialists. Over decades, this pattern reinforces itself. Data accumulates where study is frequent, making those places even more attractive for further work. Instruments are calibrated for conditions already sampled, and training programs reference sites with abundant records. The result is not deliberate neglect, but a gradual leaning, like a plant growing towards steady light. Scientists aware of this imbalance have begun to widen their focus. proposing surveys that include trenches once bypassed. Advances in mapping technology allow broader coverage, and international collaborations share resources that a single institution might lack. With each new descent, unfamiliar contours come into view, and the quiet trench gains a clearer presence in scientific charts. Still, reputation changes slowly. Names that entered public awareness generations ago continue to echo, repeated in classrooms and media alike. They serve as landmarks in collective thought, guiding interest even when other locations hold equal or greater mystery. The difference is not in the seafloor itself, but in the history of attention directed toward it. Thus, the contrast between these trenches reflects a human pattern as much as a geological one. Exploration follows stories, and stories follow what is already known. Where notice gathers, journeys multiply. Where notice is faint, discovery waits with patient composure. Far out in the Pacific, the lesser visited trench remains as it has always been, shaped by forces indifferent to recognition. Research vessels pass more rarely above it, yet its depths continue their slow transformations, unobserved yet unchanged. In time, as curiosity turns and resources shift, more eyes may look its way, and its name may grow more familiar in the language of science. Until then, it rests beyond the busiest routes of inquiry, neither hidden nor revealed, simply present. Charts hold its outline, instruments await their turn, and the water above drifts on in quiet procession, as if aware that attention, like tide, arrives according to cycles larger than intention. Lines appear on charts long before anyone sees the landscape they describe. These lines are not drawn from sight but from echoes, delicate reflections of sound sent downward and gathered again after touching the hidden terrain. Mapping the trench relies largely on sonar, a system that releases pulses and listens for their return. Each pulse travels through water, strikes the seafloor, and rebounds toward its source. By measuring the travel time, instruments calculate depth and shape, translating invisible contours into patterns of light and color across digital displays. Yet sound does not move through the ocean unchanged. Temperature, salinity, and pressure alter its speed, bending its path as it travels. In deep regions where layers differ subtly, a signal may curve away from its intended course. When that happens, the returning echo suggests a surface that is slightly misplaced, as though the landscape had shifted while no one watched. Steep trench walls complicate this process further. Instead of reflecting pulses directly back, sloping rock can scatter them sideways, sending fragments of the signal off at angles. Receivers gather what returns, though parts of the original message never come back. The resulting map holds faint uncertainties, soft distortions that must be interpreted with care. To refine these measurements, researchers deploy autonomous underwater vehicles, small robotic explorers that travel close to the seafloor. Guided by internal navigation systems, they glide along pre-planned paths, releasing their own sonar signals at shorter range. Because they operate nearer to the terrain, their readings resolve finer details, tracing ridges, ledges, and sediment fans that distant instruments might overlook. These vehicles move slowly, conserving energy stored within compact batteries. Their journeys can last many hours, sometimes days, before they rise again carrying stored data. Once recovered, their recordings are combined with earlier surveys, each mission adding new threads to an expanding tapestry of information. Even with such technology, blank spaces remain. Some areas are too steep for safe passage, others too narrow for clear acoustic returns. In certain places, Overlapping echoes create patterns that resist interpretation, like handwriting layered upon itself. Scientists mark these regions cautiously, noting depth ranges rather than precise figures. Patience guides the work. Mapping a trench is not a single expedition, but a gradual accumulation, a process of revisiting, comparing, and refining. Over time, uncertainties shrink as multiple passes confirm or correct earlier impressions. The chart evolves much as the seafloor itself evolves, shaped by successive layers of observation. What emerges is not a perfect portrait, but a close approximation, faithful in broad form, yet still softened at the edges. The unseen landscape reveals itself piece by piece, each survey illuminating another fragment of its design. Instruments translate echo into image, distance into color, silence into form, and still the deepest recesses keep portions of their outline concealed. Sound reaches down, returns, and tells what it can, while the rest remains untraced. In that remaining obscurity lies a quiet reminder that exploration is an ongoing conversation between curiosity and distance, spoken in pulses that fade gently into the vast surrounding sea. Cartographers of the deep understand that every map is provisional, a portrait drawn from echoes that may shift with the next survey. They preserve earlier versions rather than discarding them, since comparison reveals where interpretations have changed. In this layered record, certainty grows gradually, not through sudden revelation but through accumulation. Lines sharpen, slopes clarify, and scattered points join into continuous form. Yet humility remains within the practice, for the trench is wider than any data set, and its full geometry still extends beyond the reach of present soundings, known to patient minds. Far beneath the quiet surface waters, a hidden chain of volcanoes traces a distant arc parallel to the trench, its peaks buried under miles of sea, yet still shaping the world around them. These volcanoes belong to a submarine arc formed where descending crust releases fluids into the mantle above, encouraging molten rock to rise and gather in chambers that pulse with slow geological rhythm. Though unseen, this arc breathes heat into the surrounding depths. Magma does not always erupt in dramatic bursts. Often it lingers below, warming the rock and the water that seeps through cracks. As seawater filters downward, it encounters heated stone, dissolving minerals before drifting upward again, altered and enriched by its passage. Where that warmed water emerges, hydrothermal vents take form. They appear not as flames, but as shimmering springs, releasing streams dense with dissolved metals and gases. The surrounding fluid curls and billows as it mixes with the near-freezing ocean, creating plumes that rise like translucent banners before fading into the dark. These plumes carry iron, manganese, sulfur, and other elements drawn from deep within the crust. For a time they remain suspended, spreading outward in slow clouds that mark the water with faint chemical gradients. Instruments passing through them record subtle shifts in temperature and composition, delicate signatures that reveal activity below the seafloor. Even a small increase in warmth can shape this environment. Pockets of heated water gather in hollows and along ridges, forming gentle oases where conditions differ from the vast cold around them. The change is slight by surface standards, yet in these depths, a few degrees can influence circulation, chemistry, and the distribution of living cells. The volcanic arc therefore acts as a quiet architect. It does not dominate the trench, yet it contributes to its character, supplying heat and dissolved material that drift across the basin. Over long spans, these contributions accumulate, altering sediments and nourishing microscopic communities that depend on chemical energy rather than light. Geologists tracing this influence rely on sensitive detectors lowered from research vessels. These devices listen for faint thermal anomalies and measure traces of dissolved compounds. When their readings shift, they point toward unseen sources, guiding attention to regions where the crust remains active beneath its cover of water and sediment. The presence of such hidden volcanism reveals that the trench is connected to deeper planetary cycles. Melt generated far below travels upward, transfers heat, releases minerals, and then cools again, completing a slow exchange between interior and ocean. Nothing about this process is hurried. It unfolds with the patience of stone, steady and enduring. Within that stillness, warmth and cold exist side by side. The broader water column holds its low temperature, yet nearby currents may brush against a rising thread of heat before continuing on. The meeting leaves no mark visible to eyes, only a subtle change carried onward through the flow. So the darkness here is not uniform in character. It contains gradients and boundaries shaped by forces hidden beneath the crust. Volcanic energy, softened by distance and depth, moves quietly through the trench, reminding careful observers that even in the most remote reaches of the ocean, the interior of the planet continues its gentle conversation with the sea. Subtle mineral grains settle from these plumes onto the trench floor, forming thin layers that record each pulse of warmth like rings within stone. Scientists who study such layers read them as chronicles, learning when the ark stirred, when it rested, and how steadily this hidden fire has shaped the deep. Quietly, it continues shaping the unseen world below always. Temperature governs the pace of existence in ways seldom noticed at the surface. In the trench, warmth is almost absent, and the water holds steady just above its freezing point, close to 0 degrees Celsius. This chill does not arrive in gusts or waves. It remains constant, a still presence surrounding every surface and organism alike. Such cold alters matter quietly. Metals contract as their atoms draw nearer, tightening structures and increasing brittleness. Polymers stiffen, losing flexibility that might otherwise cushion stress. Lubricants thicken until they move reluctantly through narrow channels. Devices lowered into this environment must be designed with these shifts in mind, since materials chosen for temperate conditions may behave very differently when immersed in such persistent chill. Electronic components respond as well. Chemical reactions within batteries slow, reducing the rate at which energy can be delivered. Engineers compensate by selecting chemistries suited to low temperatures or by insulating power cells to preserve a trace of warmth. Even so, every circuit operates within narrower margins, its performance shaped by the surrounding cold. For living organisms, the influence is deeper still. Metabolism, the network of reactions that sustains life, depends on molecular motion. When temperature falls, molecules drift more slowly and reactions proceed at gentler rates. Inhabitants of these depths therefore live according to an unhurried rhythm, their growth measured in long intervals rather than rapid bursts. Cells adapt by producing enzymes structured to function efficiently despite reduced motion. These specialized proteins remain flexible at low temperatures, allowing chemical transformations to continue. Membranes also change composition, incorporating lipids that stay fluid in the cold, so nutrients and signals can pass through without obstruction. The result is a style of life that favors patience. Creatures conserve energy, move sparingly, and often reach maturity only after many years. Longevity can increase under such conditions, since slower metabolism reduces wear on tissues. Time itself seems stretched, not in perception but in biology, as processes unfold at a measured pace. The surrounding water reinforces this steadiness. Near freezing liquid is dense and stable, resisting vertical mixing. This stability maintains the cold, preventing warmer layers from drifting downward. Thus, the environment preserves its own character, holding temperature within a narrow range across vast distances. Researchers studying samples from these depths note how consistently they reflect this thermal influence. Chemical reactions in collected sediments proceed slowly, even after retrieval, as though the chill lingers in memory. Instruments record minimal variation across seasons, confirming that the trench remains insulated from surface fluctuations. In such a realm, change rarely hurries. Materials endure prolonged stress without relief from warmth. Organisms follow cycles tuned to scarcity and stillness. Even decay advances gradually, slowed by conditions that restrain microbial activity. Everything abides by the same quiet law imposed by temperature. This persistent cold does not announce itself with sensation, yet its effects shape every detail. It determines how metals flex, how cells divide, how energy is spent and conserved. Through it, the trench maintains a tempo unlike that of sunlit waters, a tempo measured not in moments, but in spans that stretch calmly onward. Within that measured tempo, existence becomes a study in endurance. Structures last, reactions wait, and living forms persist through intervals that would seem prolonged elsewhere. The cold holds them gently, not as an obstacle, but as a condition, and under its steady influence, the deep continues its slow and patient unfolding through ages. Sound becomes a traveler in the deep, moving through water with a steadiness that light can never match. In the trench and the vast plains around it, vibrations glide outward for immense distances, guided by the physical properties of the sea itself. Low-frequency tones, in particular, journey far, their long wavelengths bending gently rather than scattering, allowing them to cross entire ocean basins before fading. The structure of seawater encourages this passage. Variations in temperature, salinity, and pressure create layers that influence how sound refracts, curving its path instead of letting it disperse. At certain depths, these conditions form channels where acoustic waves become trapped, reflecting between layers and continuing onward, like whispers carried along a corridor. Marine researchers place listening instruments in these regions, hydrophones sensitive enough to register motions smaller than a drifting grain. They record the distant rumble of shifting crust, the calls of migrating whales, and the subtle friction of currents sliding past uneven terrain. Each sound arrives as a pattern of pressure changes, later translated into visual traces that resemble delicate calligraphy. Among these recordings, some signals have seemed unusual at first hearing. Deep tones lasting several seconds, or rising sweeps that echo across wide frequency ranges, have appeared within the archives. Their origins once puzzled analysts, not because they were unnatural, but because they traveled so far from their source that direction became difficult to determine. Over time, careful comparison revealed that such sounds arise from ordinary processes magnified by distance. An iceberg fracturing thousands of kilometers away can release a resonant pulse that journeys through the oceanic channel and arrives with surprising clarity. Submarine landslides, volcanic tremors, or even large storms, transferring energy into the water, can produce signatures that cross vast stretches before being detected. The deep ocean acts as both conductor and amplifier, preserving low vibrations while filtering out higher ones. By the time a signal reaches a sensor, it may bear little resemblance to its point of origin, stretched and smoothed by the passage. Analysts learn to read these altered forms, identifying their sources through subtle clues in rhythm and pitch. For those who study these records, the abyss is never truly silent. It speaks continuously in tones too low for human ears, a slow symphony composed by shifting earth, moving ice, and circulating water. Instruments listen patiently, gathering these notes and preserving them for later interpretation. Even biological activity contributes to this distant chorus. Certain marine animals produce calls that carry astonishingly far, using frequencies chosen by evolution for efficient travel. Their voices join the geologic murmurs, blending into a layered soundscape that spans continents beneath the surface. Understanding these acoustics allows scientists to monitor remote regions without direct presence. By tracking the arrival times of specific signals at multiple hydrophones, they can estimate where an event occurred and how strong it was. In this way, sound becomes a guide, revealing activity in places too deep or distant for immediate observation. What once seemed mysterious resolves into patterns shaped by physics and environment. The strange tones recorded in the Pacific prove not to be anomalies but expressions of familiar forces transmitted through an unfamiliar medium. Each one is a message carried patiently across water, shaped by distance yet faithful to its source. So, the abyss listens and speaks at once, receiving vibrations and sending them onward through its layered corridors. Though no ear can hear them directly, these sounds persist, traveling calmly through the immense dark, reminders that motion everywhere leaves a trace, and that even the most remote depths remain connected through the language of waves. Design begins long before a vessel touches water, in quiet rooms where measurements are considered with deliberate care. Every descent into great depth is first imagined through calculations, sketches, and models, each detail weighed against the conditions waiting far below. Engineers approach the task not as builders of machines alone, but as negotiators with natural forces that never relax their hold. For crude exploration, the central chamber is often shaped as a sphere formed from thick titanium. This geometry distributes external load evenly, allowing stress to flow around the hull rather than gather at any single point. Titanium is chosen for its combination of strength and resistance to corrosion, its crystalline structure maintaining integrity even under immense compression. The finished sphere resembles a sealed world, compact yet capable of sheltering delicate life within. Around that core, buoyancy must be achieved without reliance on hollow tanks that would collapse. Instead, designers use syntactic foam, a composite filled with microscopic glass spheres embedded in resin. Each tiny sphere encloses a pocket of gas, and together they provide lift while remaining solid to the touch. Even when subjected to extraordinary pressure, the material compresses only slightly, preserving enough displacement to keep the craft neutrally balanced in the water. Power presents another challenge. Batteries must supply energy for propulsion, lighting, instruments, and life support, yet chemical reactions inside them slow as conditions grow more severe. Engineers select cells that deliver steady output despite environmental strain, and they calculate capacity with caution. Every system is assigned a budget of stored energy, and that allowance must cover descent, operation, and ascent with reserve remaining. Weight is considered with equal precision. Every added component increases mass, which demands more buoyancy, which in turn requires more structural material. Designers therefore evaluate each bolt, wire, and panel, retaining only what serves a clear purpose. The craft becomes a study in balance, where function justifies presence and simplicity enhances reliability. Safety margins govern all decisions. Structures are tested beyond expected limits, sometimes in massive pressure chambers that simulate conditions of the deep. Measurements confirm how metal flexes, how seals respond, how joints behave under sustained load. Only when these trials demonstrate resilience far exceeding planned depth is a vessel cleared for use. Such caution reflects the understanding that repair is impossible once descent has begun. Every mechanism must operate correctly the first time, without adjustment or replacement. Redundant systems stand ready to assume control if primary ones falter, and release mechanisms are designed to function even if power fails. Reliability is not an aspiration but a requirement shaped into hardware. Communication equipment, navigation sensors, and environmental monitors are all enclosed within housings built to withstand compression. Transparent viewports are formed from specialized acrylic or quartz, their thickness calculated so that stress spreads evenly across their curved surfaces. Even small imperfections are unacceptable, since uniformity ensures that force remains balanced. As assembly concludes, the craft embodies a quiet partnership between human ingenuity and physical law. It does not conquer the environment it enters. Instead, it conforms to it, shaped according to principles discovered through study and experiment. Each material, curve, and circuit represents a decision guided by respect for conditions that cannot be altered. When such a vessel finally descends, it carries with it the sum of those decisions. The ocean exerts its influence as it always has, steady and immense, while the machine answers with equal steadiness, its structure prepared for every demand. In this exchange, engineering reveals its purpose, not defiance, but harmony, allowing exploration to proceed within boundaries drawn by nature itself. Preparation for descent often begins not in water, but in stillness. Before entering the vessel, explorers spend time inside mock cabins built to match its interior exactly, sitting within curved walls that leave little room to stretch or turn. These rehearsals are not tests of endurance alone. They are introductions to the scale of the space that will soon surround them for many hours. Inside the actual sphere, movement is economical. Knees rest near panels, shoulders brush equipment, housings, and every object has a fixed place. The design is intentional, allowing essential systems to remain within reach without wasted motion. Once sealed, the chamber becomes a small world containing breath, thought, and observation, its boundaries defined by metal rather than horizon. Time passes differently in such an enclosure. Without external reference, minutes gather quietly into longer spans. The mind adjusts by attending to details, the glow of readouts, the soft shift of posture, the cadence of one's own breathing. Awareness narrows, not from constraint but from concentration, as attention settles on the instruments that describe the unseen surroundings. Trust in those instruments is fundamental. Displays translate depth, orientation, and environmental conditions into numbers and symbols that must be accepted without hesitation. Training ensures that each indicator is understood thoroughly so that a single glance conveys meaning. Confidence grows from repetition, from learning how every gauge behaves during routine operation and during simulated faults. Such preparation includes deliberate exposure to unexpected scenarios. Instructors introduce altered readings, delayed responses, or simulated system failures, guiding trainees to respond calmly and methodically. The goal is not speed, but clarity, the ability to interpret information and act with steady precision. Familiarity transforms potential confusion into practiced sequence. Psychology receives as much attention as mechanics. Specialists study how confined environments influence perception and mood, noting that limited space can heighten sensitivity to sound and motion. Candidates learn techniques that maintain composure, steady breathing patterns, measured speech, and deliberate pacing of tasks. These habits create an inner rhythm that remains stable regardless of external conditions. Isolation also becomes a companion. Communication with the surface may be intermittent, and long intervals can pass without exchange. During these stretches, occupants rely on their training and on each other, maintaining quiet dialogue and shared awareness. The absence of outside voices does not signify absence of connection, only a different form of it, one sustained by preparation and trust. Physical comfort is carefully considered as well. Seats are shaped to support the body for extended periods, and clothing is chosen for flexibility and warmth. Nutrition is planned in small portions that can be consumed easily, while hydration is managed to balance need with practicality. Every aspect of human presence is accounted for, as though the vessel itself were an extension of its occupants. Through such measures, the experience becomes less an ordeal than a discipline. The sphere is no longer merely a container, but a workspace shaped to support concentration. Within it, observation replaces distraction, and awareness becomes finely tuned. The explorers carry their composure with them, as essential as any instrument mounted beside them. When descent begins, all this preparation accompanies them, unseen yet active. Training guides each motion, knowledge steadies each decision, and confidence in design allows attention to rest on discovery. In that quiet chamber, human perception and crafted technology join, forming a partnership that allows presence in places where no unprotected life could remain. And within that partnership, patience becomes the strongest tool, sustaining thought and observation until the moment of return arrives gently. Beneath the shifting crust, a slow exchange unfolds that links the ocean floor to the air above the continents. It proceeds without spectacle, guided by pressure, heat, and time, yet its influence extends across ages far longer than human history. This exchange is part of the planet's carbon cycle, a circulation that moves carbon between surface and interior through pathways hidden from sight. Sediments settling along converging plate boundaries often contain carbon locked within minerals or the remains of microscopic organisms. As tectonic motion carries these layers downward, that carbon travels with them, descending gradually into the mantle. The journey is unhurried, measured in centimeters each year, though the total distance eventually spans hundreds of kilometers. During this descent, some of the carbon remains trapped in solid form, stored within altered rock that sinks ever deeper. This process acts as a long-term reservoir, removing carbon from the atmosphere and oceans and holding it within the planet's interior. Over spans of millions of years, such storage influences the balance of greenhouse gases that shape global climate. Not all of the descending material stays below. Heat and pressure transform portions of it, releasing carbon-bearing fluids that rise through overlying rock. These fluids may feed volcanic systems, returning carbon dioxide to the surface through eruptions or diffuse emissions. Thus, subduction both stores and releases carbon, participating in a cycle that balances removal with return. The timing of these exchanges is vast. Carbon drawn downward today may not reappear for tens of millions of years, emerging only after its host rock has traveled deep within the mantle and later melted or fractured. This delay creates a stabilizing effect, smoothing fluctuations that might otherwise alter atmospheric composition more abruptly. Geologists studying ancient rocks find evidence of this process recorded in mineral structures and isotopic signatures. These clues reveal that plate boundaries have regulated carbon levels throughout Earth's history, moderating extremes of heat and cold. When subduction rates increase, more carbon can be carried inward, gradually lowering concentrations near the surface. When volcanic release dominates, carbon returns, allowing temperatures to rise. Trenches therefore play a quiet role in climate, not through immediate weather but through long cycles that guide planetary conditions. They serve as gateways through which surface material enters the interior, beginning journeys that will shape the atmosphere of distant eras. Each fragment carried downward becomes part of a slow conversation between crust and mantle. This exchange does not operate alone. It interacts with biological activity, ocean chemistry, and continental weathering, all of which influence how much carbon reaches subduction zones. Together, these processes form a network of feedbacks, adjusting the distribution of carbon among air, water, and rock. The system functions without central control, its balance emerging from countless gradual interactions. In this way, the trench participates in climate not as a dramatic force, but as a patient steward. It receives, stores, and occasionally returns the elements that regulate planetary warmth. Its contribution unfolds so slowly that no single generation can witness the full arc, yet over geologic time, the effect is unmistakable. Far below the waves, stone continues its descent, carrying within it traces of ancient atmospheres and vanished ecosystems. Those traces will remain hidden until distant ages release them once more. Through such quiet cycles, the planet maintains continuity, adjusting itself across epochs while life evolves upon its surface, unaware of the deep processes that help sustain its world. Far below the reach of drifting plants and sunlit currents, nourishment arrives only in faint installments. Particles descend from distant waters, fragments of organic matter released far above, settling slowly until they reach the trench. Each speck carries stored energy, though by the time it arrives, much has already been consumed along the way. This gradual rain forms the foundation of the deep ecosystem. Microbes, small invertebrates, and delicate scavengers rely on these scattered deposits, gathering what they can and using it with careful economy. Nothing is wasted. Every trace is processed, recycled, and passed along, sustaining a chain of life built upon scarcity rather than abundance. Because supply is limited, the structure of this community follows a narrow energy pyramid. At its base lie the microorganisms that capture and transform whatever nutrients appear. Above them exist slightly larger creatures that feed upon these minute producers. Each successive level receives only a fraction of the energy available below, since metabolism consumes part of every transfer. In regions closer to the surface, plentiful resources allow larger animals to thrive, supported by broad foundations of food. Here, the base is slender. The amount of usable energy entering the system is so small that only modest populations can be sustained. Most inhabitants remain small, their bodies adapted to function on minimal intake. Large predators require steady nourishment to maintain muscle, movement, and internal balance. A creature of great size must eat frequently, or else it expends more energy than it gains. In the trench, such conditions rarely exist. Food does not arrive in predictable quantities, and long intervals may pass between substantial meals. Under these constraints, gigantism offers little advantage. Evolution, therefore, favors efficiency over scale. Organisms that grow slowly, move gently, and conserve resources are more likely to persist. Their tissues demand less fuel, their motions require less effort, and their survival depends on patience rather than speed. Size becomes measured not in meters but in sustainability. This pattern appears consistently across deep environments. Surveys reveal communities composed mostly of small forms, with only occasional larger individuals whose needs remain modest compared with surface-dwelling counterparts. Even the largest species found here display restrained proportions, their anatomy reflecting the limits imposed by available energy. The scarcity shaping them is not dramatic. It is subtle, continuous, and absolute. No sudden famine announces itself, because scarcity is the ordinary condition. Each organism lives within that quiet boundary from birth onward, its physiology tuned to match the supply it can expect. Researchers modeling these ecosystems calculate how much organic matter descends each year and how efficiently it can be converted into living tissue. Their figures confirm what observation suggests, that the energy entering the trench supports only a delicate hierarchy. Increase the demand, and the system would falter. Maintain balance, and it endures. So the absence of enormous hunters is not a mystery, but a reflection of arithmetic written in biology. Where energy is scarce, life arranges itself accordingly, shaping bodies that fit the available flow. The trench becomes a realm where moderation is the prevailing design, and where survival belongs to those who live within strict means. In this measured world, existence resembles a long, careful breath, drawn slowly and released just as gently. Creatures glide, feed, and rest according to rhythms set by supply rather than impulse. Through this restraint, the ecosystem remains stable, sustained by modest inputs that nonetheless suffice when every inhabitant shares the same quiet economy. Stories often grow where sight cannot follow. In places beyond ordinary reach, imagination fills the unknown with forms drawn from memory, legend, and the shapes of familiar animals enlarged beyond reason. The trench, distant and seldom visited, has long invited such visions, its hidden slopes becoming a canvas for speculation. Biology, however, traces quieter lines. Every organism must obey certain limits set by energy, structure, and chemistry. Bodies require support, tissues require fuel, and reproduction requires stable conditions. These needs do not vanish in remote environments. They remain constant, guiding what kinds of life can persist and what forms remain improbable. In deep habitats, available nourishment arrives in small amounts and irregular intervals. Creatures that thrive there tend to match their consumption to this restrained supply. Large animals demand proportionally greater intake, not only to move, but to maintain internal balance. Without sufficient resources, their systems cannot function for long. This simple arithmetic governs size, as reliably as gravity governs falling stone. Physical design adds further constraints. Tissues must withstand surrounding force. Circulatory systems must deliver oxygen efficiently, and skeletal structures must support mass without excessive energy cost. As size increases, these challenges grow more complex. Adaptations that allow survival at modest scale may fail when enlarged, since stress distributes differently through larger bodies. For these reasons, surveys conducted with cameras and sampling devices consistently reveal communities composed mainly of small or moderate organisms. Researchers analyze recorded footage, examine collected specimens, and compare findings across expeditions. Patterns repeat with steady consistency, showing diversity of form but not the presence of enormous unknown predators. Yet tales of hidden giants continue to circulate. They persist partly because absence of observation can be mistaken for possibility. When a place remains seldom visited, imagination may treat it as unbounded. Cultural traditions also play a role, preserving ancient narratives of sea creatures whose size symbolized mystery rather than measurement. Such stories travel easily, passing from voice to voice, while careful data spreads more slowly. Sound recordings, photographic surveys, and environmental DNA sampling all contribute to modern understanding. Environmental DNA analysis detects traces of genetic material suspended in water, revealing which species inhabit a region, even when they are not directly seen. Results from deep sampling match what visual surveys suggest, indicating populations of known types rather than undiscovered leviathans. Scientists approach these findings with patience, aware that knowledge grows gradually. Each expedition refines the picture, narrowing uncertainty and clarifying patterns. When unexpected species appear, they are documented carefully, their anatomy measured and compared, their place in the ecosystem considered. Discovery remains possible, yet it proceeds within the framework established by physical law. In this way, the trench teaches a distinction between mystery and myth. Mystery invites study, encouraging observation and evidence. Myth invites wonder, offering stories shaped by imagination. Both have their place, though only one describes what truly lives in the depths. So the question of hidden giants resolves not through dismissal, but through understanding. The environment sets boundaries that life must respect, and within those boundaries, organisms flourish in forms suited to their conditions. What the evidence shows is not absence of life, but presence of life shaped precisely to fit its world. The unseen remains rich with detail, filled with movements too subtle for legend, yet no less remarkable. Within that quiet domain, scale follows necessity, and necessity follows the steady rules that govern all living systems. Thus the trench holds no colossal shadows, only inhabitants perfectly proportioned to endure where they are. Within the quiet layers beneath the trench floor lies a chronicle written grain by grain. Each particle that settles becomes part of a record, not in ink or stone tablets, but in strata that accumulate slowly over spans beyond ordinary reckoning. Scientists seeking these records lower long, hollow cylinders into the seabed, drawing up cores that hold columns of sediment arranged in delicate sequence. When these cores are lifted and opened, they reveal bands of differing color and texture, each layer marking a distinct chapter in the history of ocean and atmosphere. Some bands are pale with microscopic shells, others darker with volcanic ash, others rich with minerals carried from distant continents. The order is precise, older layers resting below younger ones, preserved like pages that have never been turned. Careful analysis allows researchers to read this archive. The shells of ancient microorganisms contain isotopes of oxygen and carbon that reflect the temperature and chemistry of the water in which they formed. By measuring these isotopes, scientists reconstruct past climates, tracing shifts between warmer and cooler eras that occurred long before written history. Occasionally, a layer appears that differs sharply from those above and below. A sudden deposit of coarse grains may signal an ancient underwater landslide. A thin stripe of unusual minerals may indicate a distant volcanic eruption whose ash traveled across the sea before settling. Even subtle changes in grain size can suggest alterations in ocean circulation or continental erosion. Time is recorded here not in years, but in depth. A few centimeters may represent centuries, while several meters can encompass millions of years. As cores lengthen, they reach further into the past, offering glimpses of conditions that prevailed when continents stood in different positions and currents followed different paths. These sediments also preserve traces of life that once drifted through the water. Pollen grains blown from ancient forests, fragments of plankton shells, and microscopic fossils remain locked within the layers. Through them, researchers learn which species thrived, which declined, and how ecosystems responded to gradual environmental change. The trench serves as an especially faithful archive because its depth protects deposits from disturbance. Currents move gently there, allowing particles to settle without being stirred again. Over time, the layers compress, yet their order remains intact, maintaining continuity across immense spans. This stability grants scientists a rare opportunity to examine sequences that elsewhere might be erased. Extracting such cores requires patience and precision. Equipment must descend carefully, penetrate the sediment without disturbing its structure, and return with the column undisturbed. Once aboard a research vessel, the sample is handled with quiet attention, for even slight vibration could blur the boundary between layers. As laboratories study these materials, patterns emerge that connect distant regions of the world. A volcanic ash layer found in one trench may match a layer discovered thousands of kilometers away, confirming the reach of an eruption long past. Variations in chemical composition may align with shifts recorded in ice cores or terrestrial rocks, linking ocean history with events on land and in the atmosphere. Through these comparisons, the sediments reveal that Earth's story is continuous, each environment recording its own chapter while echoing others. The trench contributes its portion faithfully, preserving signals that might otherwise vanish from memory. Thus, the quiet mud at the bottom becomes an archive more enduring than parchment. Within it lie records of climates, currents, eruptions, and living communities, all arranged in patient succession. Those who study these layers learn to read them as historians read manuscripts, tracing meaning in texture and composition. In this way, the deepest deposits speak, telling of ancient seas and distant ages, their voices carried upward through the slender columns of sediment that bridge present and past. Nothing carved into the planet remains fixed for long, though change often unfolds too slowly for ordinary notice. The trench exists within this gradual motion, shaped not once but continuously, its form adjusted by forces that proceed with patient persistence beneath the crust. Tectonic plates drift across the mantle at rates comparable to the growth of a fingernail, only a few centimeters each year. This motion appears slight when measured against a human lifetime, yet its constancy grants it immense influence. Over centuries, the displacement becomes meters, over millennia, kilometers, and over millions of years, entire ocean basins are rearranged. Along the boundary where plates converge, the surface responds to this motion with subtle transformation. One plate descends while the other flexes, and the margin between them shifts position almost imperceptibly. The trench marks this boundary not as a permanent groove, but as a momentary expression of ongoing adjustment. Sediments accumulate, compress, and sometimes slide, altering contours that charts once recorded. Ridges form where material gathers, then flatten as pressure redistributes it. Even solid rock deforms under prolonged stress, bending rather than breaking, its shape evolving in increments too small to witness directly. Earthquakes contribute their part as well. When strain stored in rock is released, the surrounding terrain may rise or sink by small amounts. Such movements rarely redraw the landscape dramatically, yet they add to the steady progression of change. Each event shifts the arrangement slightly, continuing a process that never truly pauses. Heat rising from within the planet also influences this transformation. As material deep below warms and circulates, it alters the buoyancy of overlying crust. Sections may tilt, settle, or lift in response, modifying the trench's profile over long intervals. These adjustments occur without sound or spectacle, guided by thermal currents moving far beneath the seafloor. Measurements collected across decades confirm this gradual evolution. Repeated surveys reveal differences measured in meters or less, subtle variations that accumulate when compared across generations of data. What once seemed a fixed boundary emerges instead as a migrating form, its outline redrawn by time itself. Geological time operates on scales that stretch imagination. A century is a brief instant within it, a million years a passing chapter. Within such durations, coastlines advance and retreat, mountains rise and erode, and trenches shift position across the globe. The Earth reshapes itself through these processes with quiet consistency. For scientists, understanding this motion requires patience and comparison. Instruments placed years apart provide reference points, allowing researchers to trace displacement with precision. Patterns emerge slowly, confirming that stability is only apparent, never absolute. The trench therefore stands not as a finished structure but as a stage within a continuing sequence. Its walls, floor, and surrounding slopes exist in a state of gradual revision, molded by forces that operate whether observed or not. Every grain of sediment, every fracture in rock, participates in this long transformation. Seen from the span of a single life, the change is almost invisible. Seen from the perspective of ages, the trench is a moving feature, migrating, deepening, softening, reshaping. It is a reminder that the planet is not a static sphere, but a living system of shifting layers. And so the trench endures not by remaining the same, but by continually becoming. Beneath the still water above, motion persists, guiding the slow choreography of crust and mantle. In that unceasing movement lies the true nature of the place, a landscape written in time rather than stone, forever adjusting, forever in motion. In laboratories far from the ocean, engineers sometimes test spacecraft components inside steel chambers that seal shut with a heavy quiet. Air is drawn out until almost nothing remains, creating a vacuum that presses outward on every surface from within. Though opposite in direction, this condition shares a kinship with the immense compression found in the deepest seas. Both environments impose extreme stress, and both demand structures that can endure without flaw. Designers who study deep submersibles recognize familiar challenges when they turn their attention to vehicles meant for distant worlds. A hull built to withstand crushing force must distribute stress evenly, just as a spacecraft must prevent internal pressure from forcing its walls outward. Materials chosen for one task often inform the other, since strength, uniformity, and resistance to fatigue matter in either realm. Seals provide another parallel. In the depths, joints must prevent water from entering. In space, they must prevent air from escaping. The direction of force changes, yet the principle remains the same. Even a minute imperfection can allow leakage, and so both kinds of craft rely on precise machining and careful testing. Engineers refine surfaces until they meet smoothly, forming barriers that hold firm under demanding conditions. Temperature extremes offer further lessons. Spacecraft encounter intense cold in shadow and sharp heating in sunlight, while deep ocean machines operate in persistent chill. Insulation methods developed for submersibles, including layered materials that slow heat transfer, can guide solutions for probes traveling beyond Earth. In both cases, stability of internal temperature supports instruments and protects delicate electronics. Navigation systems also share conceptual ground. Vehicles exploring distant moons must rely on sensors rather than direct observation, interpreting surroundings through data streams. Techniques perfected in underwater exploration, where visibility is limited, and instruments provide the primary awareness to help shape these approaches. Algorithms designed to translate signals into spatial understanding can be adapted for planetary missions. One destination of particular interest is Europa, a moon of Jupiter believed to hold a vast ocean beneath its icy crust. Scientists suspect that this hidden sea may resemble Earth's deepest marine environments in certain respects, with high pressure, darkness, and chemical interactions between water and rock. To reach such a place, a probe would need to descend through ice and enter liquid depths, operating reliably in conditions that mirror those studied beneath terrestrial waters. Concepts for such missions draw upon decades of ocean engineering. Spherical pressure vessels, corrosion-resistant alloys, and autonomous guidance systems all trace their heritage to devices first created for marine research. Knowledge gained from testing equipment in Earth's harshest aquatic regions becomes a foundation for planning journeys beyond the planet. The connection extends beyond machinery. Experience gained by scientists who interpret data from remote instruments teaches patience and precision, qualities equally essential when signals arrive from distant worlds after long delays. Methods of analyzing faint readings, filtering noise, and confirming results through repetition form a shared language between oceanography and planetary science. Thus, the study of the deep sea becomes a rehearsal for exploration elsewhere. Each descent into extreme conditions refines understanding of how materials behave, how systems endure, and how information can be gathered where direct presence is impossible. The ocean serves as a proving ground, offering challenges that echo those found in space. Through this quiet exchange of knowledge, boundaries between disciplines soften. Lessons learned in one environment illuminate another, revealing that exploration follows common principles wherever it occurs. Whether descending beneath waves or traveling toward distant moons, engineers rely on the same careful balance between curiosity and preparation. In this way, the hidden ocean below and the hidden oceans beyond become linked, not by proximity but by insight. What is discovered in one realm guides progress in the other, and the patient study of Earth's depths helps open paths toward worlds still waiting in the dark. Knowledge of the trench exists in fragments, like scattered pages from a book whose full story has yet to be assembled. Charts outline its general form. Instruments have traced portions of its slopes, and samples have revealed glimpses of its inhabitants, yet wide stretches remain unmeasured, their contours known only through inference. Survey vessels have mapped certain corridors with precision, though between those paths lie expanses that have never been directly scanned. Sonar passes require time, fuel, and careful navigation, and even long expeditions can cover only limited ground. As a result, large sections of the trench persist as blank spaces within scientific charts, waiting for future measurements to bring them into clarity. Within those uncharted reaches, the distribution of life remains largely unrecorded. Specimens collected so far represent only the locations where instruments have touched down or cameras have drifted. Beyond those points, communities may differ in composition, density, or behavior, shaped by subtle variations in chemistry and terrain. Each unexplored pocket holds the possibility of organisms not yet described, adapted to conditions unique to their narrow range. Biologists recognize that deep ecosystems often contain species with extremely limited habitats. A ridge, a mineral deposit, or a small change in water composition can support populations found nowhere else. Until such places are sampled, their inhabitants remain unknown, existing quietly beyond present catalogs. The absence of data does not imply emptiness, only distance from observation. Geological processes also retain unanswered details. Although measurements indicate how plates converge and how sediments accumulate, the exact structure of rock layers far below the seafloor is still interpreted through indirect signals. Seismic waves provide clues, though their paths can be complex, bending through materials of varying density. From these patterns, scientists construct models, refining them as new readings arrive. Certain questions concern timing. The precise rate at which sections of crust descend, the intervals between major shifts, and the long-term evolution of the trench profile are understood broadly but not in full detail. Long records are needed to resolve such patterns, and those records require patient monitoring across decades. Even chemical conditions hold uncertainties. Water samples reveal dissolved elements and compounds, yet concentrations may vary across small distances or change gradually over time. Without continuous observation, these fluctuations remain only partly known. Instruments placed for extended study provide insight, though their coverage is limited to specific sites. Researchers approach these unknowns not as obstacles but as invitations. Each gap in knowledge marks a place where discovery can occur, a reminder that exploration is a process rather than a finished achievement. The trench offers information slowly, revealing its nature piece by piece as technology improves and expeditions return. Past investigations have shown how often new findings appear once an area is examined closely. A single survey can uncover features previously unsuspected, altering understanding of surrounding regions. Such moments demonstrate that the unseen may hold complexity beyond expectation, awaiting only the means to be perceived. Thus, the trench remains partly veiled, its outlines sketched yet incomplete, its inhabitants partly listed yet far from fully known. What has been learned forms a foundation, though above that foundation stretches a wide horizon of unanswered detail. In that expanse lies the continuing story of inquiry, guided by curiosity and sustained by patience, as observers return again and again to listen, measure, and record what the depths gradually choose to reveal. Language in science is usually careful and restrained, shaped to describe rather than to dramatize. Yet on rare occasions, a word appears that seems to carry more weight than the rest. When researchers speak of certain environments as terrifying, they are not confessing fear in the ordinary sense. They are acknowledging a precise reality, one defined by conditions that allow no forgiveness for mistakes. In technical discussions, this word signals an understanding that the setting grants no second chances. Equipment must function perfectly, calculations must be exact, and preparation must be complete before entry begins. If any element fails, the surrounding forces do not pause or lessen. They continue unchanged, indifferent to intention or effort. Such language reflects experience gathered over decades of exploration. Engineers, pilots, and scientists who have worked in extreme environments learn to recognize where tolerance exists and where it does not. Some places permit improvisation, offering time to correct an error. Others respond instantly to weakness, exposing flaws the moment they appear. The latter are described with terms that convey respect for their strictness. In these regions, safety depends entirely on foresight. Materials must be chosen with full knowledge of their limits, and those limits must exceed expected conditions by generous margins. Procedures are rehearsed until they become instinctive, ensuring that responses arise smoothly even under strain. The word terrifying becomes shorthand for this demand for perfection. It also acknowledges imbalance. Human technology operates within boundaries, while natural forces often extend beyond them. Machines are designed with care, yet they remain temporary constructions, subject to wear and uncertainty. The environment, by contrast, maintains its intensity continuously without fatigue or distraction. When scientists use strong language, they are recognizing this difference in endurance. The term, therefore, carries a specific meaning inside research communities. It does not describe panic or dread. Instead, it conveys that a setting is unforgiving, that it offers no margin for oversight, and that it will reveal weaknesses immediately. It is a concise way to express that nature holds the advantage, not through hostility but through constancy. Students encountering this vocabulary sometimes expect tales of danger or drama. What they discover instead is a culture of caution and preparation. Experienced explorers speak calmly, emphasizing checklists, redundancies, and verification. Their tone remains measured, yet their word choice signals the seriousness of the conditions they study. This seriousness fosters discipline. Knowing that an environment will not accommodate mistakes encourages meticulous planning and thoughtful design. Instruments are inspected repeatedly, calculations reviewed, and assumptions tested. Each step is taken with the awareness that reliability must be achieved before the journey begins, not after. Over time, the word itself becomes part of professional language, understood without elaboration. Colleagues recognize its implication and adjust their expectations accordingly. It serves as a reminder that some frontiers cannot be approached casually, and that success depends on aligning human effort with the realities of the natural world. Thus, when scientists describe a place in this way, they are expressing respect rather than alarm. They are stating that the conditions demand precision, patience, and humility. The word stands as a compact description of an environment where accuracy is essential and resilience is tested. Within that understanding lies a quiet acknowledgement of partnership. Exploration proceeds not by overcoming such places, but by working within their rules. The terminology reflects this relationship, revealing how knowledge grows when observation meets restraint. Through careful language, researchers communicate the character of the world they study, conveying in a single word the balance between curiosity and caution. From orbit, Earth appears serene, its clouds drifting softly above continents and seas, its surface giving Andy calm as though governed by gentle balance. Seen this way, it can seem as if the planet rests comfortably within human understanding, mapped, measured, and named. Satellites trace its outline, instruments record its cycles, and cities glow across its nights, suggesting a world thoroughly known. Yet far below that tranquil image lies a different reality, one that does not bend to human plans or perceptions. In the depths of oceanic trenches, forces operate that no technology can soften or redirect. Pressure, temperature, and geological motion proceed according to their own laws, unaffected by observation or intention. These conditions remind researchers that knowledge does not equal command. The belief in mastery has grown gradually through centuries of discovery. Each new chart, each successful expedition, and each refined instrument has extended human reach, creating the impression that the planet yields its secrets steadily and completely. Progress in science and engineering has indeed expanded what can be explored, allowing entry into places once thought unreachable. Still, there remain boundaries that cannot be crossed simply through determination. Exploration requires not only curiosity, but compliance with natural constraints. Materials must endure, forces they cannot alter, and explorers must accept limits set by physics rather than ambition. In regions where conditions exceed those limits, presence becomes impossible regardless of intent. The trench illustrates this principle with quiet clarity. Its environment continues unchanged whether studied or ignored, maintaining its intensity without variation. Instruments sent into such places function only if they conform exactly to surrounding conditions. Should they fail to do so, the environment does not adjust to accommodate them. It remains constant, while the human creation yields. This contrast reveals how control is often an interpretation rather than a fact. On the surface, people redirect rivers, cultivate land, and construct vast structures, shaping local surroundings to suit their needs. These achievements can create the sense that nature has been subdued. Yet beneath those achievements, planetary processes continue undisturbed, operating on scales far beyond daily awareness. Geological forces move continents, circulate heat through the mantle, and reshape terrain across ages. Such processes neither resist nor assist human activity. They simply continue, guided by principles older than life itself. When measured against these vast cycles, individual accomplishments appear as brief episodes within a much longer story. Scientists who work in extreme environments come to recognize this perspective through experience. Their instruments reveal conditions that cannot be negotiated with, only understood. The realization does not diminish curiosity. Instead, it refines it, encouraging approaches grounded in respect for what cannot be changed. This understanding gradually replaces the notion of domination with one of participation. Exploration becomes less about conquest and more about observation, less about altering the world and more about learning its patterns. The trench stands as a quiet teacher in this regard, demonstrating that the planet retains domains where human influence is limited to careful study. Even the most advanced technology must operate within boundaries defined by nature. Devices can be strengthened, calculations refined, and procedures improved, yet none of these steps removes those boundaries. They only allow brief and measured entry into environments that remain fundamentally independent. Thus, the idea of complete control fades when considered alongside such places. The Earth is not an object shaped entirely by human will, but a system whose deeper workings continue beyond reach. Recognition of this truth does not lessen achievement. It places achievement within context, showing it as part of a relationship rather than a conquest. In that relationship lies a quieter form of understanding, one that values knowledge without assuming authority. The trench, silent and distant, affirms this perspective simply by existing, a reminder that the world holds realms where nature leads and humanity follows with attentive steps. Night passes across the ocean surface, though far below, no change accompanies it. The passage of hours overhead leaves the depths untouched, as if time itself moves differently there. While continents rotate towards starlight and cities dim into sleep, the trench continues in its own steady rhythm, unchanged by the turning world. Deep within the crust, tectonic plates persist in their gradual motion. Their movement is silent and continuous, a slow convergence that never pauses. Rock descends, bends, and transforms under strain, guided by forces older than any landscape above. This motion has carried on for ages beyond memory, and it continues now with the same patient consistency. Around that shifting boundary, pressure remains constant. It presses inward from all directions, steady and unrelenting, shaping every particle and surface within its reach. Nothing in that realm escapes its influence. Structures endure it, sediments compact beneath it, and living cells adapt to it. The force does not intensify or relax with passing hours. it simply persists. Within that environment, microscopic life carries on its quiet activity. Single cells drift or rest upon mineral grains, drawing energy from chemical reactions that unfold slowly in surrounding water. Their existence depends on processes measured in minutes and hours, yet their lineage stretches across epochs. Generation follows generation without interruption, sustained by conditions that have remained stable for immense spans. These organisms require no sunrise to guide their cycles. Their metabolism responds instead to temperature, chemistry, and the availability of dissolved compounds. Each reaction proceeds according to the laws of physics and chemistry, forming a continuous chain of transformation. Though unseen, these processes represent a form of motion as real as the shifting of stone. The darkness surrounding them remains complete. Light from above never reaches this depth, and nothing within the trench alters that absence. The blackness is not a momentary state, but a permanent condition, constant through centuries. Creatures that live here perceive their surroundings through touch, vibration, or faint chemical traces rather than sight, inhabiting a world defined by senses other than vision. Water itself moves gently through the trench, guided by differences in density and temperature that steer deep currents along the seafloor. These flows are slow and steady, circulating nutrients and dissolved minerals from one region to another. Even in apparent stillness, motion persists, subtle yet continuous, linking distant parts of the ocean through gradual exchange. Above, weather shifts, tides rise and fall, and winds cross the surface. None of these changes disturb the deeper realm. The trench exists apart from such variations, its conditions governed by factors far removed from daily fluctuation. It remains consistent, while the world above cycles through seasons and storms. Instruments that have visited these depths record this constancy. Their readings show that temperature varies little, pressure holds steady, and chemical balances change only slightly over time. Such measurements reveal an environment defined not by sudden events, but by endurance. Stability, rather than activity, becomes the dominant characteristic. Thus, tonight, as on countless nights before, the trench continues its long, quiet existence. Plates move, forces press, microorganisms live, and darkness endures. Nothing announces these processes, yet each persists with unwavering continuity. The scene does not reset with dawn or dusk. It simply continues, unbroken. In this steady persistence lies a sense of scale that extends beyond ordinary awareness. The trench is not a place of moments, but of durations, where change unfolds slowly and constancy defines experience. While time passes swiftly for those above, below it settles into a deeper cadence, one measured not by clocks, but by the enduring motions of the earth itself. Legends once imagined unknown depths as places where extraordinary creatures might dwell, concealed from sight and waiting beyond reach. Such visions linger in cultural memory, shaped by centuries when vast regions of the world remained unexplored. Yet, as instruments have descended and returned with records, the hidden reality has revealed itself in a different form, one less mythical, yet no less remarkable. What lies within the trench is not a realm of gigantic beings, but a landscape defined by extremity. Conditions there exist at the edge of what matter and life can withstand. Temperature, chemistry, and mechanical force combine in ways rarely encountered elsewhere, creating an environment that tests every structure placed within it. Even minerals respond slowly to this intensity, altering shape or composition as years pass. Within that severity exists a delicate balance. Fragility accompanies endurance, not as a contradiction, but as a partner. Organisms adapted to such surroundings possess bodies tuned precisely to their setting. Their membranes, proteins, and internal chemistry operate within narrow tolerances. A small shift in pressure or temperature can disrupt these systems, showing how finely adjusted their existence must remain. This precision gives the trench an atmosphere of unpredictability. Although many conditions remain steady over long spans, small variations can produce significant effects. A slight change in sediment flow, a subtle alteration in chemical concentration, or a gentle shift in underlying rock may influence which organisms thrive and which diminish. These changes occur quietly, without spectacle, yet they reshape local ecosystems over time. Life here therefore exists close to its limits. Each cell functions near the boundary of what biology can support, maintaining stability through specialized adaptations. Enzymes fold in ways that resist compression. Membranes contain molecules that preserve flexibility, and metabolic pathways proceed at measured rates. Survival depends on these adjustments working together continuously. Scientists studying such organisms often describe them as examples of possibility rather than exception. They demonstrate how living systems can extend into conditions once thought uninhabitable, expanding understanding of biology's range. Yet their presence does not suggest boundless resilience. Instead, it highlights how carefully life must match its surroundings in order to persist. The trench thus conceals truths more subtle than legend imagined. Its hidden character is not defined by spectacle but by nuance, by the interplay between severity and adaptation. What is concealed there is a record of limits explored and met, of structures refined until they function precisely within demanding circumstances. Observations gathered from past descents have gradually replaced speculation with evidence. Cameras reveal forms shaped by necessity, samples show chemistry tuned for stability, and measurements confirm the constancy of surrounding forces. Each discovery adds detail to a portrait that grows clearer while retaining its sense of depth. Understanding this reality changes the meaning of what it means for something to be hidden. Concealment does not imply drama or threat. It can signify complexity awaiting recognition, patterns awaiting interpretation, and relationships awaiting explanation. The trench holds such concealed intricacy, layered and patient. In this way, what is truly hidden there is not a creature or a secret in the ordinary sense. It is a demonstration of nature operating at its margins, where endurance and delicacy exist side by side. The unseen becomes a lesson in balance, showing how existence can persist even where conditions approach their most exacting form. So the depths contain no monstrous guardians, only living evidence of adaptation carried to its finest edge. Within that stillness, life continues quietly, sustained by harmony between structure and environment, revealing that the greatest mystery is not size or strength, but the subtle persistence of living systems at their limits. A final stillness settles as the descent reaches its imagined end, not an arrival but a pause within an ongoing world. The trench remains where it has always been, vast and patient, holding its depth without effort. Its scale does not announce itself loudly. Instead, it lingers in quiet awareness, a measure of distance so great that ordinary reference fades. Earlier glimpses have traced fragments of its story, hints of shifting crust, drifting particles, and delicate organisms continuing their lives far from daylight. These impressions gather now like distant constellations, forming a single wide picture. The mind holds them gently, sensing how each detail belongs to a larger pattern that stretches beyond sight. The magnitude of that pattern rests not only in distance, but in endurance. Pressure surrounds every surface there, constant and unwavering, yet within it structures persist. Minerals hold their form, instruments function for a time, and living cells carry out their silent chemistry. Survival unfolds not through resistance, but through alignment, each element shaped precisely for the conditions it meets. Such endurance reflects a principle repeated throughout the natural world. Where circumstances seem most severe, adaptation refines itself most carefully. Life does not overwhelm its environment. It listens, adjusts, and finds a way to continue. In this balance lies a quiet resilience, one that depends on harmony rather than force. Above those depths, the planet turns steadily, carrying oceans and continents through cycles of light and shadow. The surface changes from hour to hour, yet far below, darkness remains unaltered. It is not an absence, but a presence, a constant backdrop against which all activity unfolds. Within it, processes continue that require no illumination, guided instead by chemistry and time. The earth itself shares this constancy. Beneath landscapes familiar to daily experience, layers shift slowly, heat circulates, and matter transforms. These movements rarely reveal themselves directly, yet they shape the world across ages. The trench is one expression of this hidden activity, a place where the planet's interior conversation approaches the boundary of the sea. To reflect on such places is to sense how small a portion of the world is visible at once. Most of its story unfolds quietly, beyond ordinary perception. Exploration offers brief windows into that hidden expanse, moments when instruments and imagination together illuminate what would otherwise remain unseen. Each glimpse deepens understanding while preserving the vastness that still lies beyond reach. The descent now becomes a return, not upward through water, but outward through thought, carrying with it impressions gathered along the way. Depth gives way to distance, and distance to memory. What remains is an awareness of scale, of persistence, and of the subtle ways life endures within demanding surroundings. Long after attention turns elsewhere, the trench continues its patient existence. Plates shift, elements circulate, and microscopic forms carry on their quiet exchanges. Nothing there pauses for observation, and nothing concludes when observation ends. The processes simply continue, steady as the turning of the planet itself. If this journey has stirred a sense of calm curiosity about the hidden workings of the world, you are welcome to linger with that feeling a little longer. There are many more quiet frontiers waiting to be explored in thought and imagination, each offering its own gentle perspective on the vast and intricate earth we share.